A quick remark. In this lesson, we're gonna be talking about structures, but before that, I've got some good news. A brand new version of Visual Studio just came out, Visual Studio 2026. So if you've been using Visual Studio 2022 up to this point, go ahead and uninstall it and get the new one. I've already done that myself, and from now on, all my lessons will be recording using Visual Studio 2026. How do you do that? Just open the Visual Studio installer. There you can remove the versions you already have installed. In that same window, there is a tab that shows you a list of all available versions. Look for Visual Studio 2026 Community. If you don't see it there, just download the latest installer from Microsoft's official website. Type Visual Studio 2026 into the search bar and install it from there. It's a bit of a shame that all the previous lessons were made in Visual Studio 2022 because now they're slightly outdated. But don't worry, in the new version, only the interface has changed a little, everything else basically works the same. So you'll figure it out in no time. Let's start the lesson. Hey everyone, here comes another big lesson that's really going to change the way you write your code, because today we're going to learn our very first custom data type, structures. Up until now, you've only been using the built-in data types, variables, constants, arrays, pointers, references. But starting with today's lesson, we're going to create our own data types. First, let's talk about why we need them in the first place. Imagine you're writing a program that works with a collection of cars. A car in your program has several characteristics: weight, name, year of production, and top speed. You could represent that with 4 separate variables, but we don't just need one car, we need a bunch of them. Naturally, you'd think, okay, I'll store them in an array. But you can't make an array of cars because the data type car doesn't exist yet. So instead, you end up creating 4 separate arrays, and each index in those arrays logically corresponds to one specific car. And then, whenever you need to work with all the cars, you have to remember or look up the names of all those arrays. Now imagine that you also need several more arrays. An array of cars that go faster than 200 kilometers per hour, an array of cars of a specific brand, an array of cars from a particular year, and so on. Suddenly, you've got a whole bunch of arrays, and each one needs its own meaningful name. It becomes a mess very quickly. But if we had a data type called car, the code would look much cleaner. We'd just create one array, fill it with cars, and then simply work with that one array whenever we needed any of their characteristics. That's why we need to be able to create our own data types in programming. In C++, just like in many other languages, you're allowed to create your own data types. Usually, these are simply combinations of built-in data types or combinations of both built-in and custom types. In C++, the custom data types include structures, which we're learning today, unions, enumerations, and classes. We'll go over the first 3 in this lesson and next 2. The main thing to understand is this. When you create your own data type, it means you can create variables, constants, arrays, pointers, and references of that type in exactly the same way you've been doing with types like char, double, int, and so on. Let's move on to the structure itself. I'm going to give you a definition that we'll stick to for the entire lesson. I'm intentionally simplifying the functionality of structures at first so it's easier to get familiar with them, and later I'll explain what I left out. So in C++, a structure is a named group of data of different types. If an array is a type that stores only one kind of data and the elements don't even have their own names, then a structure can store several variables, or even just one variable, and those variables can be constants, references, pointers, arrays, or even objects of other structures. Let's start learning this definition by actually working with a structure in code. First of all, if you want to create a structure, you need to define the structure type first. In other words, you need to declare the type of the structure. Usually this is done in separate files, but we haven't learned how to work with multiple files yet, so for now, we'll define our structure types right inside main.cpp. The syntax for creating a structure type is the following. You write a keyword struct, which is short for structure, then you write the name of the structure type. It's common practice to name your own types using Pascal case, meaning each word starts with a capital letter. After that, you open curly braces, and at the end, you absolutely must put a semicolon. Notice that we don't put a semicolon after function definitions, but here we do. Inside the structure, you place the actual data. This can be variables, constants, arrays, pointers, or references. The important part is that each field must be declared by specifying its type and its name, followed by semicolon. We're going to define our structure types at the very top of the file, above the function prototypes. Later, when we learn how to work with multiple files, we'll move these type definitions out into separate files. Here's the first example. This is an empty structure because it doesn't contain any data. By the way, all the data inside a structure is called its fields. You might notice that in my editor, all structure fields are highlighted in orange. That's a new color compared to what we've seen earlier in the course. Your editor may show them differently, although you can change that in the settings. Now, is there any point in creating empty structures? Yes, there is, but we won't be dealing with that here, and that topic is definitely not for beginners. Here's the next, more useful structure. It's called point. This structure describes a point in a three-dimensional coordinate system, so it has three fields, the coordinates x, y, and z. The next structure should already look familiar. This one describes the car from earlier in the lesson. Each car will have its own name, weight, year, or years of production, and top speed. The following structure describes a student. They have a first name, last name, and age. And the last structure describes a school class. It has a pointer to an array of students. Right now, the pointer doesn't point anywhere, but it can. And a value that stores how many students there are. I wrote all these examples to show that the data inside structures can vary widely. Some structures only contain int variables, some contain both an array and several variables of different types, some contain two arrays, and some even contain a pointer to another structure type. So, like I mentioned earlier, a structure can contain any amount of data of any types. Now let's move on to creating objects of these structures. Everything we did before was just creating the type, not the actual objects that exist in memory. So let's talk a bit about terminology, because people can call these things in all sorts of different ways. To work with structures, you first have to define the structure type, and only then you create the structure objects. These objects are sometimes just called structures or instances of a structure. Personally, I prefer the word object, so that's the term I'll be using from now on. How do we create a structure object? Exactly the same way you've been creating any other kind of data up to this point. If you want to create a variable of a structure type, just write the name of the type and then the name of the variable. Remember what a variable is. It's data whose value can be changed. In this case, you're creating an object whose fields you're allowed to modify. Want to create a constant? Just put const at the beginning and everything else stays the same. Type name, then the name of the constant. After that comes list initialization, but I'll explain that separately in another section. What's interesting is that when you create a constant structure, you technically don't have to initialize it. You can delete that part of the code and the compiler will still allow it. Why? Because there's something called a constructor inside the structure, even if you don't know about it yet. When we get to constructors, I'll come back to this point. For now though, don't rely on that. Always explicitly initialize constant structure objects using list initialization. Here we have an array of structure objects. Here we have a pointer to a structure. And here we have a reference. In other words, creating structure objects works exactly the same way as creating data of the standard types. The only thing that stands out a bit is initialization, but we'll talk about that separately. Now let's move on to working with structure objects, specifically with the fields of the structure because that's where the actual values are stored. Let's take our car structure for now and create a variable of that type. The first question is, what values do the structure's fields have when the object is created? The answer is the same as any regular uninitialized variable, garbage values. To see that, we first need to learn how to access the fields of a structure object. To do this, you write the name of the object, then a dot. That dot is the member access operator. Once you type it, your IDE will usually show a hint with all the fields you can access. Then you just write the name of the field you want, and that's it. Now you can assign a value to it and read from it. For example, if we try to read the fields of an uninitialized structure object, we'll get an error at compile time. But if we assign a value to a field first and then access it, we'll see the value successfully. Notice that you can use structure fields just like regular variables. Here I'm assigning the value of a structure field to a normal variable, and here I'm passing a field's value into a function. Now let's move on to initializing a structure. Sure, we could create a structure object and then manually assign a value to every field one by one. But it's much more convenient to initialize the fields right when we create the object. We actually have three ways to do that. The first one is aggregate initialization. You've already seen this with arrays. When you create a structure object, you can write the assignment operator and then in curly braces list the values for its fields separated by commas. The first value goes to the first field, the second value to the second field, and so on. If you provide more values than the structure has fields, you get a compile time error. If you provide fewer values, the remaining fields will get their default values, not garbage. Let's run the code and take a look at the output. The second option is to use default member initializers. When you define your structure type, you can assign default values directly to its fields. Basically, you're specifying the values that any object of this structure will have when it's created. Doing this is simple. You just assign values to the fields right inside the structure definition. And you don't have to do this for every field, only for the ones you want to have defaults. Below, I create two objects. The first one will use the default member initializers, and the second one will use the aggregate initialization you already know. Then I print the fields of both objects to the screen. Let's run it and see what happens. There is also a third, more modern way to initialize structure objects: designated initializers. They allow you to initialize fields by name, not by order. To use them, you still write the assignment operator and curly braces, but now you put a dot, then the name of the field, and then its value. What's the advantage over aggregate initialization? The main benefit is that you can specify fields in any order. Imagine your structure has a lot of fields and you only need to initialize one of them, but that field happens to be somewhere in the middle. Let's say it's the 7th field. You can't go into the structure definition and rearrange anything, so with designated initializers, you just write the name of the field you want to assign a value to it. All the other fields will automatically get their default values. Now let's move on to another topic, copying structures. First, let's recall how copying works for the other data types you already know. Here we have two variables. Using the assignment operator, we copy the value of one variable into the other. Nothing complicated. It works the same way with constants, no difference at all. It's also the same with pointers, except remember that the value of a pointer is the address of the variable it points to, so after copying, both pointers store the exact same address. With references, things are different. A reference is just an alias for an object, so when you copy a reference, you're actually just referring to the same object. Technically, references aren't copied, they are simply bound to the same object. With arrays, copying is not allowed, so we have to copy them manually using a loop, going element by element. So what about structures? Take our first simple structure as an example. I won't explain it again because it's very straightforward. Below, I created an object of that structure and initialize it. Then I create another object and use the assignment operator. How does copying work here? This kind of copying is called shallow copying, and it simply copies the values of each field from one structure to the other. The two structures must be of the same type, otherwise you'll get a compile time error. And if we print the fields afterward, we'll see the same values in both objects. But here's an interesting detail. If I create a structure object first, and only after that assign it the value of another object, structure object, the assignment operator in my editor changes color. Why? Because in this case, a custom overloaded assignment operator is being called. It's implicitly generated inside the structure. In my Vim, all methods are highlighted in that color. You don't know about operator overloading yet, so don't worry. Just know that everything still works the same way. It's still shallow copying. So why is this called shallow copying? Let's move on to the next example and I'll explain. We have a simple structure that represents a number stored on the heap. It has one field, a pointer to that number, and in main, I create an object of this structure and initialize that single field. I assign the pointer a heap address and set the value of that address to 5. So what do we have? On the stack, we have a structure object that contains a pointer, which means the pointer itself is on the stack. But that pointer points to a variable on the heap, whose value is 5. Then I print out the dereferenced pointer and we see the value 5. Next, I create another object and copy the first one into it. What gets copied here? The value of the field. And the value of our pointer field is simply an address. So now both structure objects have pointers that point to the exact same heap variable. If we run the code, everything seems fine at first, but it's not. Each pointer was supposed to point to its own separate variable. Let's delete the heap variable that the first object's pointer refers to. Then we try printing the value from the second object's pointer again. Run it, and what do we see? Garbage, because the whole time there was only one variable on the heap. And that is what shallow copying means. It just copies the values of all fields, including pointers. There is no new memory allocated. But there's also deep copying, something the programmer has to implement manually. If the structure only contains regular fields that store numbers, then a normal assignment is fine. But if the structure contains pointers, then you need to write code that creates a new variable on the heap and copies the data into it. Only then do you get proper deep copying. So keep this in mind. If your structures contain pointers, simply using the assignment operator to copy them is not enough. Alright, now that we know how to create structures and how to use them, let's start moving them around and doing different things with them. For example, we can create a pointer to a structure. The syntax is the same one you already know. We have a structure called person, which has a name and an age. Here I created a structure object and initialized it. Then I created a pointer to that structure. So how do we work with it through the pointer? And why would we need to do that in the first place? Here's why. Structures are often stored on the heap because they can take up more space in memory than simple variables. And if something is stored on the heap, you can only work with it through pointers. Up to this point, we worked with pointers. It was usually with simple numbers or characters. Sometimes we made pointers to arrays or strings, and the main operation we used with pointers was dereferencing, getting the value the pointer refers to. So what happens when we dereference a pointer to a structure? We get the structure object itself, and we can work with it and its fields. But then, why do we get an error like in this example? We're trying to access a field of the structure after dereferencing the pointer. That should work, right? The problem here is operator precedence. The member access operator, the dot, has higher precedence than the dereference operator. So the compiler tries to apply the dot to the pointer itself. And a pointer is not a structure, which is why we get the error. So we need to raise the precedence of dereferencing. How do we do that? With parentheses. We wrap the dereference in parentheses, so we get the structure first and then access the field. Now we can change the value of the field to 5, and if we print that field, we'll see the number 5. This operation, accessing a structure's fields through a pointer, is so common in C++ that the language provides a special operator to make it easier. It's called the member access through pointer operator, and it looks like an arrow. It's just a hyphen followed by a greater than sign. This operator works exactly the same way as the parenthesized dereference version. It just requires fewer characters and reads more naturally. So keep this in mind. If you see the arrow operator, it means there's a pointer to a structure on the left and the structure's field name on the right. If you see a dot, then on the left is the object itself, not a pointer. You can also create references to structures, and working with them is even simpler. You already know how to create a reference. You write the data type, then an ampersand, then the name of the reference, and then you bind it to an object. In this case, you don't need to use the address of operator to get the address of the structure object. And when you're working with a reference to a structure, you don't need to use the arrow operator. The dot is enough, because everywhere you use the name of the reference, it's treated as if you're using the actual object itself. So technically, the dot is used on the object. The reference is just another name for it. References to structures are actually more common than references to simple numbers. The reason is that structure objects are often passed into functions, and if you pass them not by reference or pointer, they will be copied using shallow copying. Because of that, you won't be able to modify the structure's fields, and at the same time, you'll end up with another large object sitting on the stack. We'll go over function parameters a bit later. First, you should know that you can create constant structure objects. To do that, you just write const before the type. But what's the difference between a regular object and a constant one? With a regular object, you can initialize its fields and then change their values as many times as you want. But if the object is const, then you can only assign values to its fields once. After that, any attempt to change them will be blocked by the compiler. Unlike with other data types like numbers or arrays, you're not required to initialize a constant structure object immediately. In that case, its fields will receive either garbage values or default values, or values you specified with default member initializers. Since a structure is a type, that means you can create arrays of structures. You do this the same way you create any other array. You write the data type, then the name of the array, then the size, and optionally you can initialize it. Here, each element of the array is its own structure with its own fields. We can initialize each field of each array element like this. When you want to work with an element of the array, you first write the name of the array, then the index inside square brackets. In the case of structures, what you get is a structure object, and then you can use the dot operator to access its fields. Notice that we don't need any extra parentheses here because the array indexing operator has higher precedence than the member access operator. So you get the correct object first and then access its field. Let's run it and see what we get. Like I mentioned earlier, structures are usually placed on the heap because they often contain many fields and each of those fields takes up memory. So structure objects are much heavier than simple numbers or arrays of numbers. And to avoid filling up the stack, we allocate them on the heap instead. Which means we need pointers again. We create a pointer to a structure object and then we allocate the actual object on the heap. If we want, we can even initialize it right there during allocation. And after that, we work with a pointer just like we normally would. Just don't forget that if you create structure objects on the heap, you must delete them when you're done with them using the pointer. Remember what a function declaration is? It's when you write the return type, function name, its parameters, and then a semicolon at the end. This tells the compiler, hey, somewhere in this project there is a definition of this function. The linker will find it if it's needed. Just remember what the function looks like so you don't complain when I use it in this file. Right now we're writing our function declarations above main and the actual function definitions below main. Later, when we learn how to work with header files, we can move our function prototypes into one file and the actual function definitions into another. Well, structures can also be declared and defined. Up to this point, we've been writing definitions of structures. To declare a structure, all you have to do is write struct followed by the structure's name and then a semicolon. If you want to define the structure, then you include the curly braces and place the fields inside, optionally with default values. Why would you ever need to declare a structure? For the exact same reason as with functions. Imagine we have a function that takes a reference to person. Why does the compiler currently know what fields the structure has? Because the compiler reads the file from top to bottom, it first sees the structure definition, remembers its fields, and then understands how to work with it later. If we completely remove both the declaration and the definition, the compiler simply won't know what person is. If we leave only the declaration, then the compiler will know that person is a structure type, but it won't know anything about its fields. This is called an incomplete type. Now imagine that the function definition is located in another file, and here we only have its declaration. In that case, the function doesn't use the fields of the structure here, so the compiler doesn't actually need to know what those fields are. If we leave only the structure declaration, there will be no issue because the compiler knows that the type exists. Later, when we start spreading structures and functions across multiple files, I'll show you a much clearer example of when and why structure declarations are useful. Right now, since everything is still inside a single file, this is mostly just preparation for the future. Since a struct is a data type and the fields inside it also must have data types, you can put objects of one struct inside another. Here's an example. We have the familiar person struct. I also created another struct called class, which consists of a teacher and an array of students. The array will have a dynamic size and a pointer to it allocated on the heap. So here we have an instance of one struct inside another, and that's a normal practice. In main, I create a pointer to class on the stack, and then I allocate the actual class object on the heap. I initialize it like this. First, I assign values to the teacher's fields, then I specify the size of the student array, and then I fill that array, which is also located on the heap. Then I want to print the teacher's name and age. I have a pointer to the class, so I use the arrow operator to access its teacher field. But teacher is itself a struct object, so I use the dot operator to get its fields. First the name, then the age. And you can have as many nested accesses like this as you want. After that, I output information about each student. I again use the class pointer to access the student's field. Then field is an array of person object. So I use indexing to access a specific student, and then using the dot operator I get the fields I need from that student. When I'm done working with the class, I first delete the internal pointer to the student array and only then delete the pointer to the class itself. If I just delete the class pointer right away, the teacher object, the size field, and the pointer to the student array will be removed from the heap, but the student array itself will remain there, causing a memory leak. That's why you always delete memory in the reverse order of how you allocated it. Structs can actually be defined without a name. And yeah, that sounds a bit strange. Look at the first struct definition I'm showing here. It doesn't have a name, even though it has fields. So what's the point of a struct like that if we can't create objects of it? Normally, to create an object, you need to specify the type, and in this case, there is no type name. The thing is, when you define a struct, you can immediately create objects of that struct right after its closing brace. Take a look at the second definition. The struct has a name, but right after the closing bracket, we can list variables of that struct's type. Here I created a normal variable, an initialized variable, an array of 3 variables, and a pointer to an object of that struct type. You may notice that they're all shown in brown in my editor. If you remember, that means that they're stored in the global scope, which means that they're placed in static memory. In other words, this is the same as defining the struct first in global scope and then declaring all of these variables separately afterward. Now let's go back to our nameless struct. Even if your struct doesn't have a name, you can still create objects of it right there, immediately after the definition. Those objects will have that struct's type, and you can work with them in your code just fine. But you still won't be able to create new variables of that type later. Why would you ever use something like that? In rare cases, it's convenient for one-off aggregates or small local chunks of data where you don't need to reuse the type name. Think of it as deliberately limiting the scope. Here is the struct, and here are the only objects of that struct. That's it. It also prevents your namespace from being cluttered with another type name. For example, if you already have a struct called point, you can't use that name again in the same scope for something else. So sometimes anonymous structs help avoid naming conflicts. But again, anonymous structs are very uncommon. You're very unlikely to write your own anonymous structs on purpose. You might come across them at some point, but you rarely need to create one yourself. You can also define structs not only in the global namespace but inside functions as well. That also sounds kind of ridiculous, and it really is a rare thing to do. Personally, I've never seen it used anywhere in real code, but you can do it, so why not show how it works? And it's actually simple. Here's a function, and here's a struct definition that I placed inside that function. What's the catch? The only difference is that now you can create variables of that struct type only inside this function. This limits the struct scope, so the name point, for example, is free to be used for something else in other parts of your code. Is this a common practice? No. Should you be doing it? Definitely not. Let's talk about something more useful now. A struct is a data type, which means that when writing functions, we can use structs as parameter types. We can also pass struct objects into functions and even return them from functions. Let's start simple. What happens if we have a function and we pass a regular int to it? We know that when we call a function, the argument is passed by value, for example, the number 100. The function creates its own parameter variable that gets initialized with this value. We change it to 10 inside the function finishes, and that parameter gets destroyed. The original variable from main stays unchanged. It still equals 100. This is called passing by value. We can also make the function take a pointer. In that case, when we call it, we pass the address of the variable. The function creates its own pointer parameter, which holds that address. We dereference it, access the value stored at that address, change it, and as a result, the original variable changes. When the function ends, the pointer gets out of scope. That's passing by address. And finally, we can use references as parameters. In that case, we simply pass the variable directly, the function creates a reference bound to it, and we modify the variable through that reference. This is passing by reference. So in C++, we can pass objects to functions by value, by address, and by reference. And all of this applies to structs as well. Let's use our familiar person struct. We have 3 functions. One takes the object by value, one takes a pointer to it, and one takes the reference to it. In main, I create an initialized object of this struct and start passing it to these functions. When we pass a struct by value, what happens? A copy is made. All of Damian's data gets copied into the parameter person. The function works with a copy, and when it ends, the copy is destroyed. The original object stays unchanged. So here's the first recommendation. If your struct is larger than the size of a reference, larger than 8 bytes on x64 systems, avoid passing it by value. Why? Because passing by value duplicates the entire object in memory, and structs are often much larger than basic data types. But if your struct fits into 8 bytes or less, passing by value is fine because there's practically no difference in performance compared to passing by reference. Now let's look at passing by address. In this case, the function creates its own pointer that points to the original object. Using that pointer, the function can modify the object's fields directly. So the next recommendation, if you want to pass just a single struct object into a function, prefer passing by reference instead of by pointer, because with pointers you need to use arrow instead of dot, which means more typing and more visual noise. However, if you're passing an array of structs, pointers are usually the right tool, the same way we do with arrays of int, double, and so on. The third option is passing by reference. This also avoids copying, so no extra memory is used, and the syntax is simpler. And one last recommendation. If your function should not modify the struct's fields, make the parameter a constant reference. That way, the compiler prevents accidental modification. For example, my initialize function modifies the object, so the reference is non-const. But my show function only reads data, so the reference should be const to protect the original object. Same goes for arrays of structs. If the function needs to modify the elements, keep the pointer non-const. If it only reads them, use a pointer to const. This is standard practice. We've got one last thing to cover, the size of structs and why it's not always equal to the sum of the sizes of their fields. Remember the sizeof operator? It lets us check how many bytes a struct actually takes up in memory. Let's start simple. If a struct has only one field, then the size of the struct is the size of that field. Here's the first example. The struct has only an int, which takes 4 bytes. So the struct itself takes 4 bytes, straightforward. The second struct has 3 char fields. Each char takes 1 byte, and there's nothing unusual here. The struct will take 3 bytes total. When fields are placed one after another and all of them have the same size and alignment requirements, the size of the struct is just the sum of the field sizes. But now things get more interesting. Let's look at the third struct. It has 2 fields, a double and an int. A double is 8 bytes and an int is 4 bytes. You might think the total is 12 bytes, but in reality the struct takes 16 bytes. Why? Because memory is laid out according to alignment rules. Each type has an alignment requirement. It has to start at an address that's a multiple of some number of bytes. For double, that number is 8. Since double is the most demanding type in this struct, the entire struct must be aligned to 8 bytes. The double takes the first 8 bytes, then we place the int, which needs 4 bytes, but to maintain alignment and ensure that the total size of the struct is also a multiple of 8, the compiler adds extra empty bytes called padding. That's why the total size is 16 bytes. Now let's look at the fourth struct. It has a double, an int, a char, and a bool. The largest type is still double, so the struct will be aligned on 8 bytes. The double takes 8 bytes. The int takes 4 more. Then we place char and bool, which take 1 byte each. After that, the compiler again adds some padding, so that the final size of the struct is a multiple of 8. So even though the field sizes are different, the final size of this struct is also 16 bytes. So the general rule is the size of a struct is rounded up to the nearest multiple of its largest alignment requirement, and padding bytes may be inserted between fields to satisfy alignment. Why does this matter? Because the CPU reads data more efficiently, and sometimes only correctly when values start on properly aligned addresses. The compiler arranges fields so that each one begins at a valid address, and the total size is aligned so that elements in arrays of this struct also start on aligned boundaries. Put simply, alignment and padding aren't wasted space. They're the cost of correctness and performance. Those alignment boundaries ensure that each field and each struct in an array starts at a memory address the CPU can work with efficiently. But that's not everything there is to say about structs. For example, you can put functions inside structs, and those functions are called methods. Struct can also inherit from other structs, and there are many more things you can do with them, but we'll get to all of that once we move on to object-oriented programming and start learning about classes. So I will return to structs later and finish what we started. Right now you already have plenty of information to work with. And that's it for this lesson. Thanks for watching. If you liked the video, feel free to hit the like button, leave a comment, subscribe to the channel if you haven't yet, donate via the link in the description, or become a channel sponsor to get access to practical lessons. Goodbye.